Welcome back to Differential Calculus. In this video, I want to talk about the average value of a function. Before I get there though, I wanted to do a quick refresher on the average value of a set of numbers and a very different way of thinking about that concept that you should already be familiar with. Let me get my head out of the way and let's consider a list of numbers. All right, how about the numbers 2, 3, 5, and 6? We'll make this really simple. Right, the average value, statisticians call it the mean value. Often it's represented with an x with a bar over it, simply read as x bar. And you calculate it by adding the numbers together. 2 plus 3 plus 5 plus 6, dividing by the number of values that we have, 4 of them in this case. And when you add 2 plus 3 plus 5 plus 6, you're going to get 16. 16 divided by 4 is in fact 4. So the average value of this set of numbers is 4. That's old hat. You should be very familiar with how to do that. I want to look at this in a slightly different way. I want to look at this graphically. So let's set up some bar graphs. I have a bar that is 2 blocks high, a bar that is 3 blocks high, a bar that is 5 blocks high, and one more, this bar is 6 blocks high. Of course, the total area covered by these blocks is 16, and if we divide by the width of this space, which is 4, we will get the average value, which came out as 4. Another way of thinking about that, though, if I take these 3 blocks and arrange them over here to fill in the space, I can draw a rectangle, in this case a perfect square, but a rectangle is the important bit, a rectangle of the same area. The height of this rectangle is 4, which is the average value. That's the way I want to think about things when it comes to the average value of a function. There we go. One of the ways we can interpret the average value is find the area, turn that area into a rectangle, and figure out the height of the rectangle. The rectangle that has the same area as the area under the curve has the height of the average value of that curve. Mathematically, well, finding the area, so this is going to be f bar. Well, finding the area will be the integral from a to b of f of x dx. That's something we've done many a times. That gives us the total area under the curve. I want to draw a rectangle so that the area under the rectangle is the same as the area under the curve. The height of the rectangle is going to be f bar, and the width of the rectangle is going to be the same as the width of this part of the function. And if the function started at a and ended at b, then the total distance here is going to be b minus a. So to solve for f bar, I divide both sides of the equation by b minus a. And that gives me the expression for the average value of the function. As an example, let's take a look at the function f of x equals 4 minus x squared. We've looked at this particular function more than once previously. We know that it is a parabola that opens downward. It goes from -2 to +2, and sure, that points at 4, but that's not really what matters. The average value in this case, f bar, is going to be 1 over 2 minus negative 2 times the integral from negative 2 to positive 2 of 4 minus x squared dx. All right, 2 minus negative 2 is 4. We've done this integral a couple of times. I don't want to go through all of the work again. It does come out as 32 over 3. And if I multiply 1/4 times 32 over 3, I get 8 over 3. All right, 8 over 3 is 2 2/3. If I come back over to my graph, 2 2/3 would be somewhere around there. And so if I draw in my rectangle of height 2 2/3, I get a rectangle with the same area as the area under the curve in the first place. All right. That seems, I hope, fairly straightforward. The formula is very easy to use. It's just take an integral and divide by the size of the interval on which you are integrating. Saying interval and integral in the same sentence is more than a little bit challenging. And if that's where the story was going to end, it would be a little bit hard for me to justify that this is a full video. But there is a deeper idea hiding in here that I do want to talk about before we wrap up on the course. That idea is called the mean value theorem. Let's assume that we have a real valued function which is continuous on the closed interval from a to b. With just that information, it's enough to claim that there is a point C somewhere in the open interval from a to b, such that the value of the function at C is equal to the mean value of that function. I tend to think of this as a natural consequence of the intermediate value theorem, right? To draw a curve, you have to be able to go through every point. To have a mean value, the function has to have values that are bigger than the mean value and also values that are smaller than the mean value. Or if it doesn't, then every point on the function must be equal to the mean value and the function's just constant. But if there are some points above and there are some points below, well, the intermediate value theorem says that the function has to go through the middle somehow, and that gives us the mean value theorem. All right, just like the intermediate value theorem and the extreme value theorem that we've talked about previously, the mean value theorem is an existence theorem. It tells us that the point exists. It doesn't give us any indication of how to get there. We saw that in the example we just looked through. That point has to exist, right? Once we found the mean value, you can see from the graph, the mean value intersects the graph, in fact, in two places, here and also there. We have two mean values, or 2 points that give us the mean value of this graph. There always has to be at least one. 2 is not necessarily going to be the case, although it is nice. All right. With all of that out of the way, let's go ahead and end this with one for you to calculate, and we'll have a little bit of fun with some trigonometry. I'd like you to calculate the average value of the function f of x equals sine of x plus cosine of x on the interval from 0 to 2 pi. Once you've done that, I encourage you to go into Desmos or something like that, graph the function, graph the mean value, and see where those graphs intersect to verify the mean value theorem that says that, well, there should be a point where that actually happens. All right, take a couple of minutes, see what you can do with that one. I'll see you in the next video.